Hi again, everybody. Mr. Martella here, and today we are going to get into tsunamis. We're going to talk about the several stages of tsunami life, and we're going to talk about how tsunamis are generated. Okay, so let's get started. First of all, tsunamis are defined as a series of water waves triggered by an earthquake, landslide, or a volcanic eruption. A lot of people are under the idea that tsunamis are one giant wave that moves through and wrecks an area, and that is mostly not the case. Tsunamis are a series of waves, and we'll talk more about how they come onto shore here in a couple of minutes. But if you look at causes of tsunamis, I have them broken down in a little chart here. About 3 out of every 4 tsunamis on this planet are caused by underwater earthquakes, submarine earthquakes. 10% are caused by landslides, mass wasting of material into the sea. Another 5% from volcanic eruptions, which usually includes some sort of landslide or material falling into the sea. You see 2% atmospheric causes and 11% of tsunamis, we really don't know what generated them, which is interesting in itself. But we don't have time to get into that in this video. So we're going to take a look especially at a couple of tsunamis that have been caused by submarine earthquakes. If you remember back to when we learned about the 1964 Great Alaskan Earthquake, the 9.2, that generated a lot of local tsunamis from underwater landslides, material that was just sort of sitting at the edge of a hill or an undersea cliff, and the shaking simply pushed it down to the bottom of the sea. So that can cause tsunamis also. A quick introduction to tsunamis. I taught my classes the other day that tsunamis are generated by a particular type of earthquake. These earthquakes that happen at subduction zones, usually where you have an oceanic plate being pulled beneath a continental plate. So these are areas where you have oceanic continental subduction, okay? And these are the areas that generate what we call the megathrust earthquakes. So I have a simulation here, a short video from IRIS. Let's take a look at it.
Subduction zone megathrust earthquakes, the most powerful earthquakes, can produce tsunamis through a variety of structures that are missed by simple models. The basic model shows rock above the convergent plate boundary being compressed and bent as it stores elastic energy. Once friction is overcome, the overriding plate slides abruptly up the fault, causing the leading edge to heave seawater upward, generating a tsunami. This shallow angle reverse fault is called a thrust fault because the overlying plate thrusts up over the subducting plate. Let's explore different tsunami-producing mechanisms by examining 3 famous earthquakes. In 2011, the magnitude 9 Japan earthquake ruptured a fault area 500 kilometers long by 200 kilometers wide over an interval of nearly 3 minutes. Surveys of seafloor bathymetry before and after the earthquake document up to 50 meters of fault displacement at the Japan Trench. What would that look like in cross-section? During the rupture process, the overriding plate slid up the west-dipping fault plane. That uplifted the seafloor by 10 meters, producing the local tsunami that rushed on shore within 20 minutes of the earthquake, and the distant tsunami that spread over the Pacific Ocean basin. Due to effective emergency education, 96% of the citizens evacuated the tsunami inundation zone to survive this natural disaster. Next, let's examine how deformation, as well as fault displacement of the overriding plate, can produce a tsunami. The 2010 magnitude 8.8 Chile earthquake tore a rupture zone 600 kilometers long by 130 kilometers wide. Although the rupture began at approximately the same distance from the trench, there was little to no displacement at the trench as there was during the Japan earthquake. So, what generated the local tsunami that resulted in 123 deaths and produced major damage in coastal towns? Fault displacement ranged from 5 meters at the hypocenter beneath the coast to 10 meters midway to the trench, then decreased to little or no displacement at the trench. Westward displacement of the continental shelf above the plate boundary caused broad uplift of the seafloor. In addition, the change in amount of displacement along the plate boundary caused internal deformation of the overriding plate. These effects combined to uplift the ocean floor by 2 to 3 meters. This sudden uplift generated the deadly local tsunami along the coast of South America and Juan Fernandez Islands. Alerted by strong ground shaking, coastal residents evacuated to high ground. Unaware of the danger, many vacationers did not evacuate and became victims of the tsunami. Our third example introduces splay faulting during the rupture. The 1964 magnitude 9.2 Great Alaska earthquake ruptured a major segment of the eastern Aleutian subduction zone, 800 kilometers long, lasting over 4 minutes. The continental shelf and slope of the overriding North American plate was uplifted over 9 meters, while inboard areas subsided as much as 2 meters. This sudden displacement of the ocean floor generated the tsunami that claimed lives from Alaska to Northern California. Less than 2 meters of regional uplift occurred at the trench. So what caused the 9-meter uplift of the continental shelf and generated the tsunami? In this example, we will show that there were 3 contributing factors to the devastation that ensued. With few seismometers in the region in 1964, the progression of the rupture relative to the splay faults is unknown. For simplicity, we'll show plate boundary displacement branching into splay faults. During this earthquake, displacement started on the plate boundary megathrust fault, producing 2 to 4 meters of regional seafloor uplift and subsidence. However, most of the fault offset ramped up to the seafloor on splay faults like the Patent Bay Fault that was displaced 9 meters. Because displacement on steeply dipping splay faults causes larger uplift of the ocean floor, a bigger tsunami is produced, and it starts closer to shore, providing less time to evacuate. In steep-sided fjords and inlets, ground shaking caused landslides, some entirely below sea level, resulting in surges of seawater up to 50 meters high that struck coastal towns, including Seward and Valdez. This third type of tsunami took 77 lives. In these vulnerable locations, the usual drop, cover, and hold on response to ground shaking must become evacuate immediately from low ground, even during earthquake ground shaking. The tsunami-producing mechanisms illustrated here are still just a glimpse into the variety of subduction zone earthquake faulting and folding processes. The Alaska 1964, Chile 2010, and Japan 2011, as well as the catastrophic 2004 Sumatra subduction zone megathrust earthquakes, have delivered powerful lessons that rapid evacuation of tsunami inundation zones is a life-saving emergency response.
All right, so there you saw 3 different megathrust earthquakes and how that energy is moved from the ground to the water. Okay, and essentially, the more the seafloor pushes up, the bigger the wave that you're going to get. All right, essentially, there are a couple other factors there, and we'll mention them here in a couple of minutes. So, tsunami life. The United States Geological Survey suggests that tsunamis live through 4 stages. And so let's talk about them here, because that's Tsunami 101. All right. So you see here the 4 stages of tsunami life are initiation, split, amplification, and run up. So what's that mean? First, stage 1 is the initiation of the tsunami. All right. So that's going to be your initial fault slip or your underwater earthquake, right? And that is shown right here. Okay, there's your fault slip. All right. So what's going on? Near the source of the submarine earthquake, the seafloor is permanently uplifted and down dropped, like they just showed with Alaska. You had part of the seafloor that was lifted up, and then behind that, there was some that dropped down. Okay. Um, excuse me. Now, that uplifting and down dropping will push the water column up and down. The potential energy that results from pushing the water above sea level is then going to be transferred into horizontal energy, which is the actual movement of the tsunami wave. Okay, so you have the potential energy of the upward movement, and then you get that brief pause. That's your potential energy. And then as the wave comes back down to sea level, it propagates or it moves in a horizontal motion. So that's potential energy converted to horizontal kinetic energy. And that is the initiation of the tsunami. Okay? Stage 2 is called split. In the split stage, within several minutes of the initial earthquake, the tsunami is split into one part that travels out into the deep ocean. We call that the distant tsunami, and another one that travels to the nearby coast. We call that the local tsunami. So in this image here, the deep ocean would be heading out this way. That would be your distant tsunami. And this would be your local tsunami heading towards the shore. Okay. Now, the height above sea level of the two opposite traveling tsunamis is approximately half the height of the original tsunami. So, whatever the height of the original tsunami was in the initiation stage, as the wave splits, each wave is going to be half of that height. And the speed gets more complicated mathematically. The speed at which the tsunami travel will vary, and it will be calculated as the square root of the water depth. So the distant tsunami, which is going to travel through deeper water, is going to move faster than the local tsunami, which is going to be traveling through shallower water. Okay. One note to keep in mind, the deeper and the flatter that the ocean floor is, the faster these tsunamis are going to move and the more energy they're going to keep with them. Okay. So stage 1 is initiation. Stage 2 is split. And you have to imagine the split in 360 degrees, folks. All right. I'm teaching you this in a two-dimensional sort of landscape. But remember, when we say split, that thing is going to split every way and travel out 360 degrees, just like seismic waves. Amplification is the third stage of tsunami life, and it has really the most going on, okay? Several things happen as the local tsunami travels up the continental shelf. First, the amplitude of the wave increases. What's amplitude of the wave? Well, that would be your wave height. All right. So as the tsunami travels up the continental shelf, the initial wave builds height. As the initial wave builds height, the wavelength decreases. All right. So as the initial wave gets taller, the distance in between the peaks of the waves gets shorter. Okay. And that results in the leading wave getting even taller. It starts to steepen. Okay. Finally, notice that the first part of the wave reaching shore is actually a trough. It's a dip. Okay. Where the brown arrow is. Now, this is a natural warning sign of tsunamis because if you were on shore, what you would see is, well, you would feel a big earthquake. You'd be shaken all around. Then if you're standing on a shoreline and you look, the ocean is actually going to pull back. All right. And there may be hundreds of yards of sea floor. All right. You might have been swimming in water that was up to your neck, and now that water's all gone. Okay. This is a natural warning sign that a tsunami is on the way. The ocean will pull back. Don't be going out looking for seashells. Get to high ground. Okay. So that's the amplification stage. The last stage in the life of a tsunami is called run-up. And run-up is simply when a peak in the tsunami wave travels from the near shore region onto shore. Okay, so essentially, run-up is a measurement of the height of the water on shore above the local sea level. And except for the largest tsunamis, most don't result in these gigantic breaking waves, right? Rather, what happens is they come in very much like a strong and fast-moving high tide. If you've ever been to a coastal area and you notice the difference between high tide and low tide, the tides come in gradually. With a tsunami, these things would be cruising, okay? So you would have strong surges and rapid rises in sea level. And then after run-up, part of that tsunami energy is going to be reflected back into the open ocean, but it'll get scattered a little bit by the coastline. So you will get more waves that are coming from shore back out into the ocean after this. But they'll be insignificant compared to the original waves of the tsunami. Right? So that's tsunami life, 4 stages: initiation, split, amplification, and run-up. And in the next video, we will build on what we learned here, and we're going to take a look at 2 of the deadliest and largest tsunamis in history. We will take a look at Japan 2011 and the Boxing Day tsunami in Indonesia back in 2004. We'll see you then.